two problems. One is the convergence problem. The other is the representation problem. So we first consider the convergence problem. Okay, so we look at the partial sum function Sm. Okay, so this is the partial sum function. And we want to know that under what condition the partial sum function will converge at some point x. Okay, so this is our problem. Okay, and so so we know pi, and the an and bn are obtained by Euler's formula, right? So so we have we know that sorry. No, it's not. When it's go to m, sorry about that. And so this is the 1 over pi. So an is from f of so let me say that t, okay, f of t, and the cosine and t, right, times cosine in x plus 1 over pi, f of t, sine nt dt, sine and x, right? So this is by Euler's formula. So we just replace a0 by this integral, an by this integral. So this is a0. This is an. This is bn. Okay, so we just copy the Euler formula here, and then we combine them together. Okay, so we move all the integral outside. So this 1 over pi here, and f of t. Right, and we have 1/2, right, plus summation from 1 to m, and we have cosine and t, cosine and x, plus sine and t, and sine and x. Okay, everything together and t. Okay, we just do this combination together, and we know that in trigonometry we have the some identity. I think this is the difference identity. So we have cosine n t minus x. So maybe I use x minus t is better. Okay. So basically, actually, it's cosine of nx minus nt, right? So this is equal to this one. All right. So we have f of t, right? And so we define dm t to t squared. The dm t is defined to be dm x minus t. dmx going to be 1/2 plus cosine nx. Okay. So together, so we define this sum to be the d sub m of x minus t, because that is a function of x minus t. And the format here is 1/2 plus this function. Okay. And we can do we can combine them together, so that this one should be sine m plus 1. M plus 1/2 x, and this is 2 sine x over 2. Okay, and this is m plus 1/2. Here x not equal to 2 pi. If x equal to 2 pi. I think you have some experience in high school how to combine this sum into this one. I think the point is that you just this sum you multiply with sine of x divided by 2, right? Into it, and by using the product to difference conversion. You know that? I think this is a standard exercise in high school. Suppose we have a sum. Okay. So suppose the sum is equal to summation and theta. Suppose that, and so now we multiply with sine into x. Okay. So we have okay, and this one is equal to 1/2 of so that would be sine of theta plus, and so it's then minus and plus 1/2 theta minus sine and theta. Okay. Yeah. All right. So this product is equal to the half of the difference between these two, right? And because n is from 1 to m, so you can cancel, right? So this is 1/2 of something like sine by n equal to 3/2 of theta. Okay, right. So you have that, and you cancel. This is cancel. So finally, you have 1/2 sine theta minus sine. Is that okay? And so when you divide it by this one, you can have the sum. Yeah. Okay, and so because we have 1/2 here, so you cancel the constant term. All right. So I think this is the standard technique that you have been using in high school. So you have this summation. Okay. All right. So the Dm. Okay. This function is called. It's called Dirichlet kernel. Okay, so it's called the Dirichlet kernel. Right. Okay. So it's just like a convolution here, but I don't want to address too much about the convolution. So it actually, the partial sum function becomes to the integral of the product of the original periodic function and the Dirichlet kernel here. Okay, but the argument here is x minus t. Okay, so you have to know that. Once again, all right, and if we know that from the formula you can see that we know since they are periodic with period 2 pi. Okay? So they are periodic with period 2 pi. So we have the partial sum function 1 over pi. So because the integration is over one period from minus pi to pi, but because the integrand, this product, both of them are periodic function with period 2 pi. So this one we can shift a little bit. Okay, so the integration interval will be shifted by x here. Okay. So we will do this thing. Okay, so they will be invariant because the integration is also over one period. Okay, so that the value has not changed. And so we can do the change of value. So we let u to be x minus t. Okay, so it turns out to be, so if u is x minus t, so it turns out that we have this is my I x minus u, okay, and dm u minus dt here. Okay, so that again we have so basically, you can see that you can write the partial sum function as this integral or this integral, and the argument can exchange. Can exchange to here, right? They can exchange to here or here. Okay, so that is the situation. So this is partial sum functions. Okay, now, and this one, so we will split this integral to plus into two parts. Okay, here and here we will exchange that u to be equal to minus t. Okay, again by change of variable. So this one becomes 2 u to pi and the f plus u, because minus t is defined to be u, and then dm minus u and du. Okay, plus dt. Okay, but see, the Dirichlet kernel is an even function because it consists of cosine function, right? So it's even. So so we can. So this is equal to so it's an even function. Okay, and so the final result is that we can combine them together. So here we have x plus t plus x minus t times Dirichlet. Okay, so this is the final integral representation we want for the partial sum function. Okay, so the partial function itself comes to this one. Okay, but this is not a good one because that okay, remember the Dirichlet kernel actually is a sine function here. P divided by 2 sine here. Okay, so we want to get rid of this one. Okay, we want to get rid of this one. And how can we get rid of this one? Because that so the thing is that to see if this one converge, we want to know that that this integral converges if m goes to infinity, right? So Now, the trigonometric Fourier series converge at a point x in this period, even only the following limit exists. Which limit? Actually, it's okay. So if this limit exists, then the trigonometric Fourier series at the point converge. Okay. So that okay, and we claim that. So we say this is the limit in here is the same as the following limit. Okay. Okay. So basically, we can replace the denominator to this one. Because this limit is much more easier to deal with. Okay, so we claim this limit is the same as the following limit. Okay, and to see why this is true, so here is the reason. Right. We look at the difference between these two limits. Okay. So look at the difference. All right. So taking the difference of these two limits. Right, so that so we have 1 minus e minus 1 to sine, okay, and okay, so we look at the difference. Okay, we take the difference of these two limits. Okay, and we see that since the function, look at the function, the function gt defined to be 1 over t and the 0. Okay, then the function, we define the function like this one. Because if t equals 0, this is undefined, but they go to the limit 0. Why? Because when t is small, sine 2t is equal to 2t, sine t over 2 is equal to t over 2, right? And so 2 times t over 2 is t, so the difference is 0. So the limit is 0. Alright, and this function, this function is continuous. Okay, you'll find. Right, so this is a continuous function, and so it is bounded. Any continuous function on a cross interval has maximum and minimum. This is the extreme value theorem, right? In calculus, you remember that extreme value theorem. So that it's bounded. So this one is bound. Right, and so that the gt times this one, f x plus t plus f x minus t, right, or is absolutely integrable over 0 and pi. Why? Because we know the periodic function, we have assumed that it is absolutely integrable over one period, right? And so if you shift any x and integrate over just half of the period, then it's still absolutely integrable. So this is absolutely integrable. This is one, of course, is absolutely integrable. And this one has bound, right? The maximum is maybe, for example, 10,000, something like that. So this product is absolutely integrable over this one. Okay, so now, so this is, the whole thing is absolutely integrable. Okay, over 0 pi. So this is absolutely integrable. Now you time with this one. And this is the alpha, right? Alpha goes to infinity because m goes to infinity, this is goes to infinity. So by Riemann the back lemma, this limit is goes to 0. Alright? So by the Riemann the back, okay, so by the lemma, the limit in 1, 2 is 0. Okay, so this is equal to 0. It's perfect. Okay, so we mentioned the Riemann the back lemma, right? Last Tuesday. So by this is equal to 0. So the difference of these two limits is 0. So if this limit exists, then this limit also exists and have the same value, right? Conversely, if this limit exists, then this limit also exists and have the same limiting value. Okay, so that is the situation. Alright, so now but look at the limit. Look at this limit. Right, this limit can be split into two limits. 0 to delta plus the limit from delta to pi now, so we can, and we will multiply t here, so I move t to here. And this one, yeah, because the integral, the interval is from delta to pi, so that so this function is absolutely integrable over delta pi for all delta greater than 0 but less than pi. Okay? So this is absolute, because t is continuous, 1 over t is continuous over this interval, and it has a bump, just like before. So this one is absolutely integrable again. And by the Riemann bracket lemma, right? When m goes to infinity, the alpha goes to infinity. All right. So this limit is equal to 0 again. So this limit is equal to 0 by the Riemann bracket. Okay, so that the limit, this limit is equal to this limit for any delta. Very small, very close to 0, right? Okay, for any delta. So we prove the Riemann's localization theorem. Okay. All right. So let F be a periodic function with period 2 pi, which is absolutely integrable over the period. Then, so the trigonometric Fourier series generated by f will converge for a given value x in time if and only if. So we give a sufficient and necessary condition for some positive delta less than pi, so delta can be very small. The following limit exists and goes to infinity. At the time delta is 0. Two sine m plus 1/2 d by t dt. Right, so this is the economical condition. And in which case means that if the limit exists, the value of the limit is the sum of the series at x. Okay, so we have a necessary condition for the trigonometric Fourier series to converge for a given x. So this is the if and only condition. And if the limit exists, then the limit value is just the sum of the series. So we basically solve the problem. And so Riemann's localization theorem answers the convergence problem because it gives you a necessary and sufficient condition, right, for the trigonometric Fourier series to converge for a given point x. All right, and you can see that this condition depends only on the behavior of the periodic function at the vicinity of the point x. You know, this is the function, the behavior of f at the right side of x, right? And the behavior is at the left side of the x. So the local property of the periodic function give us whether the trigonometric Fourier series converge or not at the point x. Okay. So that's why it's called the localization theorem. Okay, and so the next thing is that we should find conditions that this limit exists, right? But to simplify, if we want to prove another if an only condition, right, then we will encounter difficulties because this formulation may be the simplest one. Okay, so we try to find sufficient condition to make sure that this is true. Okay, so we are trying to find simple sufficient conditions. Okay, so now, so we will consider a fixed x, right? So we fix x because we want to know whether the trigonometric Fourier series converge at this point x. Okay, so we fix that. And for any positive delta is implied, we let a function g of t defined to be right. So we define this one. So x is fixed. So this average becomes to a function of t. And this, the t is defined in this interval from 0 to delta. Okay? So now, the integral in Riemann's localization theorem becomes dt t sine okay, so this becomes to such an integral. And this integral is very famous in mathematics, which is an incidence of the Dirichlet integral. Okay. The Dirichlet integral is something like this one. Okay, so any integral from 0 to delta and the gt function defined on 0 to delta and tagged with this ratio sine alpha t divided by t. Alright, any integral like this one is an instance of the Dirichlet integral. So again, by the Riemann lemma, the following limit alpha goes to infinity if exists, okay, is the same for all okay. Right, so if you have for a given delta, the limit exists, then the same limit will exist for all delta, for all positive delta. So the limiting value will be independent of the delta if the limit exists. Right, this is from the Riemann lemma. So now. So we can see that as delta goes to 0, the behavior of this integral will be dominated by the function g at the vicinity of 0, So let's take an example to see the effect. So the example is that we let G equal to a constant. Alright, so G is a constant, or I just say here Gt equal to C. Okay? So now, so we let Gt like this one. Okay? And the limit alpha goes to infinity. So we try to compute this irregular integral, and the limit alpha goes to infinity. So we want to compute this limit. Okay, and this one is a constant, right? So we just say it's 2c divided by pi t here. Now by change of variable, this is going to alpha delta sine u and u, because we can do this way. Okay? So we can multiply alpha here and alpha here, so alpha can cancel each other, right? And by making change of variable, u equal to alpha t. Okay, so we have du and alpha is here. So this is actually becomes to what? Becomes to an improper Riemann integral, because the integration interval will goes to infinity as alpha goes to infinity, right? Right. You keep the same integral, but the integration interval becomes bigger and bigger and approach to infinity. Okay. And so this is actually is equal to 2 times c pi, right? And this is equal to this one du. Okay? And we have to interpret that this one is, this is equal to the improper Riemann integral. Right? Improper integral, by definition, is that this limit of t goes to infinity. Okay? So, because you can evaluate this one, no problem, every finite t. But then t goes to infinity, right? So this is improper integral. And we know this improper integral is equal to what? It's equal to pi over 2. Okay? We can compute that this improper Riemann integral is equal to pi over 2. Right? And so final result is that this is equal to c. Okay? Right? So the limit of this, when g is a constant, and g is a constant, the limit of this irregular integral is equal to c itself. So we can think about so that it is suggested that if G0 dot exists, right? So if the right limit of the G functions at 0 point exists, right? So t is going to 0 on right hand side. Alright, so if this is existed, so that the GT here, when delta is very small, the value of the GT in this very small interval will be very close to this quantity, right? So essentially it's a constant function with value equal to this limit. Alright, so we may think about from this example that the Dirichlet integral, so we conjecture that if this is existed, then we have the limit of alpha goes to infinity to pi. This limit should be equal to G0, the right limit. So we guess that if the limit exists, this limit value should be equal to the right limit of the function g at 0. Is that okay for you? Right. So if the limit exists, so I give you the reason why we guess that if such a limit exists, and if we know the right limit of g at 0 exists, then we have this result. Okay, so now Dini gives us useful theorem. So Dini says that suppose g is a function on 0 and delta for some if g0 plus exists, and one more condition, that gt minus g0 plus divided by t. Okay, so this ratio is absolutely integrable over 0 delta. Then the limit of the Dirichlet. Oh, I'm sorry, I forgot. Yeah, this one, sin alpha t is equal to g delta. So this is true. But we need one more condition here. That this ratio is absolutely integrable over 0. Yes. So this is the Dini's theorem. Okay. And I give a proof of this theorem in my lecture notes. And so now we will apply a Dini's theorem to give you a very general result about the convergence problem, as an answer to the convergence problem as well as the representation problem. Okay, so let's take a short break now.